In this talk, I will present the Python library ABCPy for likelihood-free inference. I will give examples of how to define a model and perform inference, as well as show how ABCPy can be easily extended to test new inference schemes. So, in order to perform approximate Bayesian computation, 4 different components have to be defined. First, you need to have the model from which you can simulate. Then you need to have a statistics and distance function. And finally, you need to define the ABC inference algorithm you want to use. In ABCPy, this structure is implemented in an object-oriented fashion. In ABCPy, you can define objects of type probabilistic model, which implement a forward simulator method. Then you have objects of type statistics and distance, which implement respectively a statistics and distance method. Finally, algorithms are implemented in objects of type inference method, which have a sample method instead. Bayesian synthetic likelihood and related methods have a very similar structure. Again, you have probabilistic model, you have summary statistics. But the difference is that the distance we use in ABC is replaced here by an approximate likelihood class. And of course, you still have some inference methods you need to use. So let's now have a look at a very minimal ABCPy example. I will consider a rejection ABC inference with a normal model. Right, first of all, a normal model takes as an input mean parameter mu and the standard deviation sigma. So we need to define priors for these two parameters. In this case, I'm taking a uniform priors over both of them. And you can see here it's very easy to define priors. Next, you need to define the model, which is normal, of course, by passing to it as an input the mean and standard deviation parameters. And we give to it a name, which is in this case ith. So let's now see how we can define the statistics. So first of all, you need to import the statistics from the library. In this case, we are using the identity summary statistics, which basically means the full dataset is used as a summary statistic. And then you need to instantiate it. Next, you also need to define the distance. In this case, again, we import it from the library and we use the Euclidean distance here. When you instantiate it, you need to pass to the distance object the summary statistics, so that when the inference scheme will call the Euclidean distance object, it will first compute the summary statistics for you. You also need to define a backend object which basically takes care of parallelization. In this very simple example, I'm using the dummy backend, which means no parallelization is needed. Finally, let's see how you can define and use the inference scheme. So first of all, you import it from the library here, and then you need to define it to instantiate. And when you instantiate it, you pass to it the model, which in this case is height, the distance, and the backend. Of course, you can also pass some random seed, which is used for ensuring reproducibility of the random number generators. Once you define the rejection ABC inference scheme, you can sample by just calling the .sample method. When you call it, you need to pass, of course, the observation which you want to use, the number of samples which you want to get, and the ABC tolerance threshold, which in this case we set to 0.5. So let's now try to run this and see what happens. So this will take very little time. As you can see, it's done already. And the results are stored in this object, journal object. So using this journal object, which we can perform some analysis. For instance, we can print the number of simulations, as well as we can show the posterior distribution which obtained. So you see, this rejection ABC scheme took 6,000 something simulations and produced this kind of posterior plots, which are obtained by KDE, of course. So let's now have a closer look at the contents of the ABCPy library. So besides the rejection ABC algorithm, we have a wide range of sequential ABC methods. The reason why we chose sequential ABC methods is that they are easy to parallelize with respect to, for instance, MCMC ABC, which is harder to parallelize. So we implemented the population Monte Carlo ABC, sequential Monte Carlo ABC, as well as some more recent ones. All of these algorithms can be used with the following ABC distances. Of course, we have the standard Euclidean distance with its summary statistics. We have the classification accuracy using logistic regression, And then we recently added a set of divergences between datasets. So we have the velocity and distance, we have the Kullback library divergence, and some others which are listed here. As I mentioned before, we also have some methods which allow you to explicitly approximate the likelihood function. Of course, we have Bayesian synthetic likelihood, we have its semi-parametric version, and we also have ratio estimation with logistic regression. All of these three methods can be used with the following samplers. We have the standard MCMC with Metropolis Hastings acceptance rate, as well as the population Monte Carlo one. Additional features of the library are easy parallelization with MPI and Apache Spark. We have also statistics learning with neural networks, which I will show later, as well as we have the method for performing model selection with random forests. So now we dive deep into how you can implement a custom model class. The example I'm showing here is taken from this ABC Pi models repository, where we list a large selection of models. So when you implement a model, you need to provide to it 5 different methods. You need to have a method for initialization, you need to have a forward simulate method, and then you need to have 3 helper methods which are used in the inference scheme in order to check everything works correctly. So let's now have a look at how we can implement the Ricker model, which again is widely used in ABC. So as you see here, we have to define a class for the Ricker model, and this class has to inherit as a subclass the probabilistic model and continuous class, which are implemented in ABC Pi. Next, you need to define the initialization function, which takes as an input the parameters of the model. In this case, we also pass to it the number of time steps we use in the Ricker model integration. And then you need to provide a name for it, which is used in the journal file. So as you can see here, the parameters are passed to this input connector object, which is used to define the graphical model so that sampling works correctly. Then inside the initialization function, you need to call the initialization of the parent class with this super function. So now you have to implement the forward simulate method. First of all, you need to pass to it the list of input values for the parameters, the number of forward simulations, and a random number generator, which is used to generate random samples, of course. So inside this method, you need to use the parameter values to generate simulations from the model. So in this case, I did not put the full simulate Ricker function here because it would be a bit too long, but I just left the structure of the function. So in this case, we have a loop over the number of forward simulations we want to use, and we put the results of each forward simulation into this list here, and we return this list. So finally, as I mentioned before, we also have a set of helper methods. We have this check input, which is used to check if the parameter values which you provide to the function are valid or not. In this case, we are just checking if the length of the input values is the correct one, which is 3 for this model. Then we have a check output model. We have a check output method, which is used sometimes to check whether the forward simulation of the model proceeded correctly. In this case, we assume everything was correctly all the time, so we just return true. And finally, you have this get output dimension function, which returns the dimension of each forward simulation. So let's now define this class by running this cell. You see it doesn't take very long. And once you define this, you can instantiate the Ricker model in the same way as the default models I was using before. So again, here I'm using a uniform prior over 3 parameters, and I'm instantiating the model with this line, very similarly to before. And after doing that, I generate an observation by calling this forward simulate function. You see here I'm passing a list with parameter values with the 3 parameters, and I'm asking to get one single forward simulation for these parameters. And you see this run correctly, and we obtain this kind of simulation which we plotted here. So we also have ways to wrap models which are defined in R, C++, or Fortran, and we provide examples for this in the documentation of ABC Pi. In a very similar fashion, you can implement new statistics, new distance, and so on. So I will now show how you can use a very useful feature of ABCPy, which is learning summary statistics for the Ricker model. So I will consider as an example how we can use the semi-automatic approach by Funnel and Prangle 2012 with neural network. So ABCPy uses PyTorch in the background to handle neural network. So learning summary statistics with neural network is done very easily with these 3 lines here. So first of all, you need to import from the library the corresponding class, and then you need to instantiate it. Once you instantiate it, it will take care of learning the summary statistics inside. So when you instantiate the class here, you need to pass to it the model you want to use. Then you can pass to it a summary statistic, which is what you want to use to transform the data before learning your summary statistics. Then you need to pass a backend, which is used again to generate simulations if you want to parallelize. And you have a bunch of other parameters which are used for the neural network training. So you have the number of epochs, for instance, here. So once this is run, you can use this getStatistics here method from this object to get the summary statistics object, which you need to use later. So let's now run this. It will take a little bit, as you see. So I will, just want to remark that here I didn't pass any neural network explicitly, and if you do that, ABCPy it will use a default neural network structure for you. But of course, you can also pass the neural network you want to use. And you can also use GPUs for training if your neural network is very large and very expensive to train by just setting CUDA equal true. And very similarly, we provide a way to learn neural network by using distance learning based approach, which we investigated in a recent paper last year. So let's see how you can use this for inference. So it doesn't change very much from before. We have already instantiated the Ricker model and we have obtained the automatic summary statistics. So what we need to do here is just define the distance function as we have done in our first example. So again, I'm using the Euclidean distance with our learned summary statistics. So very similarly to before, I need to import the backend and instantiate it. Again, I'm using the dummy backend. And in this case, I'm using the SMC-ABC algorithm. But the way to use it is very similar to the rejection ABC one. So again, you need to instantiate the SMC-ABC by passing to it the model you want to use, the distance, and the backend. And of course, you have a seed which ensures reproducibility. And finally, this line will take care of calling the sample method and perform the inference. So you have to pass to it an observation, which I define somewhere else just for the sake of brevity. And in this case, we are using 13 SMC-ABC steps, and I'm using 100 samples. And this full output equal 1 just means that I want to store into the journal file the results from all steps of the SMC-ABC algorithm. So let's now run this. It won't take too long, actually. Right, you see now it's already done. And if you want to use MPI parallelization, you just need to replace this backend dummy line with a backend MPI. So you see it's very easy to do that. So let's see now the posterior distribution which you obtain with this SMC-ABC. So I'm using the same command as before, but now I'm asking to it just to plot the single marginals, the univariate marginals, just for the sake of simplicity. And I'm putting a green line by this parameter here, a green vertical line at the parameter value we generated the observation. So we also have some methods which can be used to investigate how the inference scheme performs. For instance, we have a way to investigate the effective sample size across iterations. You see here we produce this plot which shows the effective sample size decreasing across SMC-ABC iterations, of course, as expected. So finally, the last example I want to show is how we can easily extend ABCPy to test new inference approaches. As a case study, I will use a recent work I've done, which involves scoring rules. So first of all, let's start having a recap of Bayesian synthetic likelihood. So you see in the Bayesian synthetic likelihood approach, the posterior for your parameter is defined as proportional to the prior times normal likelihood, where the parameters mean and covariance matrix of this likelihood depend on the parameter value theta. So in the Bayesian synthetic likelihood framework, at each theta value, you generate simulations from the model and you use them to estimate mu and capital sigma here. So the Bayesian synthetic likelihood approach is implemented in ABCPy within this approximate likelihood class. So in our recent work we have done, we have studied this new posterior which I proposed, which is the generalized Bayesian likelihood-free inference with scoring rules posterior. So the posterior is defined very similar to synthetic likelihood in this way. So we have the prior term, of course, and then we have an exponential of minus this object here. So here we have W is just a scalar, which is a weight factor, and then we have a scoring rule S between the distribution of the model at theta and the observation. So a scoring rule is just, for the sake of this presentation, a scoring rule is just a function between distribution and an observation. So similarly to Bayesian synthetic likelihood, in our framework we will use simulations from the model at a fixed theta to estimate this scoring rule. So you see, this approach is very similar to synthetic likelihood because we're just replacing the normal log likelihood with this term here, minus W times the scoring rule. So how can we use the inference capabilities of ABCPy for this new scoring rule posterior? So the way we do this is we define an abstract class, which subclass is the approximate likelihood one. So an abstract class is just a way to set the functions that each scoring rule class needs to implement and to have common methods. So let's have a deeper look here. So we are instantiating here, or actually defining here, a new scoring rule class, which subclass is the approximate likelihood one. And this will be an abstract class by using this meta class parameter. So this scoring rule class needs to implement the initialization method, which takes as an input the statistics calculator and the weight which we use in our posterior. Next, we define two abstract methods. So you see, these abstract methods are methods which will need to be implemented explicitly for each scoring rule which we want to define. Otherwise, if you don't implement this, you're not allowed to instantiate any objects of the scoring rule class. So we define here the score method, which is what actually computes the scoring rule. And then we have this helper method, which is the maximum value the scoring rule can get. So finally, in order to exploit the previous structure of ABCPy, which was using the approximate likelihood schemes, we just alias the score, which we compute, to the log likelihood method, which is called by the, for instance, MCMC or PMC inference schemes in order to perform inference. So the log likelihood in our scheme is just minus the weight times the score of the distribution. So let's now run this, and we have defined this scoring rule. And we now see how we can actually define an actual scoring rule class. So I'm considering here what is called as the energy score. And as you see here, this is a subclass of the scoring rule. So the energy score as an initialization method, which takes as an input the statistics calculator, the weight value which you want to use, and also takes, in this case, we also have an additional parameter which we call beta. So when you initialize it, again, you need to pass to it, you need to call the initialization method of the parent class. Next, we need to implement the score method, which is a way in which we estimate the score. And this score method takes as an input the observations and the simulations which you get from the model. The score method here uses an helper function which we also define inside this class here. And finally, you also need to implement the maximum score method, which just returns infinity here because maximum value of the score, which we get in this case, is just infinity. So by running this cell, I've now defined the energy score class. And let's see now how we can use this. So again, it's very similar to the kind of approach we have used before. I'm defining here a difference model. I'm using the univariate GNK model for the sake of this example. And again, I'm putting a uniform prior on the 4 parameters which the univariate GNK has, and I'm instantiating the model with this line here. Next, I'm instantiating the scoring rule by just calling energy score and pass into it the identity statistics. And in this case, I'm using a weight value of 0.5. So let's now run this, and I have instantiated my model and energy score. So let's now see how we can perform inference with MCMC with that. Again, so this is very similar to what I've showed before. So you can now import the MCMC inference scheme from the library with this line, and then you need to instantiate it by passing to it the model you want to use, the log likelihood function, which in this case is the energy score, and the MCMC Metropolis Hastings scheme will call the log likelihood method of the energy score object, which we implemented in the abstract class and which aliases the score method. Next, you also need to pass the backend object as well as the random seed which you want to use. And once you have implemented it, you can perform sampling by this line here. Here again, I'm passing to it the observation which I generated actually elsewhere just for the sake of brevity, and I'm using 1000 burn-in steps in my MCMC and 5000 actual MCMC steps, which will yield me 5000 samples. So let's now run this, and you see the last parameter actually sets the number of samples or number of simulations you want to use for each parameter value, and which you will use to estimate the scoring rule. So now the MCMC is performed, and we can again plot the posterior which you obtain with the same function as before. So we can, in this case, I've used this set of parameters to generate the observation I used in the inference. And again, I'm asking to just visualize the univariate marginals. So you see, this is my posterior plot, which I get here. Okay, this is not great, of course, but I've just run a very small number of MCMC steps for the sake of brevity for this experiment. And the green vertical line, again, represents the two parameter values we generated the observation. Finally, for this model, I've also tried performing inference with an increasing number of observations. And what we notice is that for the energy score, which I've implemented here, when you perform inference with an increasing number of observations, your posterior concentrates on the actual parameter value, which are these vertical green lines. And so in this plot, you have the univariate marginals for an increasing number of observations for 1 up to 100, where the dark blue is the 100 observations one, and the green light ones are instead just one observation, say. And when you instead do the same experiment for synthetic likelihood, you see that actually synthetic likelihood does not concentrate that much around the true parameter value. So yeah, I'm almost at the end of my presentation. I want just to point people to useful resources you can find online on ABCPy. So first of all, we have a GitHub repository where we release all code and where you can follow the evolution of the library. You're welcome to contribute if you want, of course. Then we have the documentation page where we have tutorials on how to get started with ABCPy, how to implement new models, how to extend the library and so on, as well as how to use the parallelization backends and to perform all possible analysis from the posterior. So finally, we also have a paper which is due to appear in the Journal of Statistical Software, in which we dive in very much details into the parallelization structure of ABCPy. So you're welcome to read that if you're interested. And to close my presentation, I just want to thank all the people who contributed in some way to ABCPy. Specifically, I want to thank Rita Bratta-Dutta from the University of Warwick, who is my PhD supervisor. Rita Bratta, together with Marcel Schongens, who is at the ETH Zurich in Switzerland, they started ABCPy. So these other people contributed to essential bits of ABCPy library. Avinash, Nicole, and Pierre, they all contributed essentially. So yeah, this is the end of my presentation. I hope you enjoyed it, and thank you so much.